You know that feeling, right? That flash of insight, the aha moment when everything just clicks and you finally solve a really tough problem. It's powerful.
Yeah, definitely.
And we see hints of this sort of in today's most advanced AI models.
Mm.
They can backtrack, correct themselves,
Yeah.
even verify their work sometimes in these complex reasoning tasks.
They can, but here's the catch, and it's a big one.
Hmm.
It's often unpredictable. It feels less like a designed capability, doesn't it? And
Hmm.
more like, well, like waiting for lightning to strike the algorithm.
Exactly. Inspiration, not engineering.
And that unpredictability is a fundamental roadblock for all the impressive reasoning chains we might see from models like, say, OpenAI o1 or Gemini 2.5 Pro, relying on these emergent, almost accidental aha moments. It makes it incredibly difficult to build AI systems that are truly reliable.
Right. Especially for the really deep, complex reasoning challenges we actually want them to tackle.
You simply can't build dependable systems on foundations that are inherently, well, unpredictable.
Yeah. It feels like sometimes they really get it, show incredible depth, and other times they just fall flat. And we haven't really had a systematic way to make them get it consistently,
Right.
on demand.
Precisely. And that's the core challenge this research paper we're diving into today really sets out to solve. They're proposing a novel, systematic approach to explicitly teach large reasoning models, or LRMs, as they call them, how to reason.
Okay. So moving beyond just hoping for those unpredictable breakthroughs towards something controllable, repeatable.
That's the goal.
All right, let's really unpack this then. Our mission today is to dig into the core innovation and the detailed methodology of this research. How exactly do they propose building more controllable, more powerful AI reasoning skills?
Well, we've pulled insights from the detailed paper itself and some related notes that really get into the weeds of aligning these fundamental reasoning meta abilities.
Meta abilities, okay.
The paper starts by framing the problem very clearly. While prior work, using things like outcome-based reinforcement learning with models like DeepSeek R1 or Grok 3.5, has shown that advanced reasoning behaviors can emerge.
The self-correction, the backtracking we mentioned.
Exactly. Things like verification, backtracking. But the critical observation highlighted in the source notes is that this emergence remains, and this is the key quote, unpredictable and uncontrollable.
Ah.
These complex behaviors are all bundled up as what they call the emergent, unpredictable behaviors, collectively referred to as the aha moment.
So we've seen models do these cool reasoning things, but we can't bottle it, can't guarantee it'll happen next time. It's like having a brilliant but temperamental artist who only performs when the mood strikes.
That's a great analogy. And for real-world AI applications, especially in domains needing high reliability, think medicine, finance, engineering, that's just a non-starter.
Yeah.
You need consistency.
Predictable performance.
Right. The paper explicitly states that relying on these emergent behaviors limits both the predictability and scalability of LLM-based reasoning. You can't scale a process. You can't reliably trigger or control.
Okay, so the challenge is crystal clear. Emergent reasoning is unpredictable, unreliable. Their big idea, then, isn't to find better ways to somehow provoke emergence, but to kind of bypass it entirely by teaching the AI the foundational skills of reasoning directly.
Yes.
This is the explicit meta-ability alignment piece you mentioned.
Exactly. And this is where a really significant academic innovation lies. They don't just say, hey, let's teach reasoning. They ground it in a classical philosophical framework.
Oh, interesting. Which one?
Peirce's inference triad, Charles Sanders Peirce. It provides a structured way to define what those core reasoning skills are.
Peirce. Okay, I remember this. Deduction, induction, and abduction. These sound like terms straight out of a logic textbook.
They are, but the paper integrates them really beautifully into a practical framework for AI. It's quite elegant.
How do they frame it?
They frame these three modes as forming a closed inferential loop for hypothesis generation, testing, and revision, mirroring the scientific method. It's a powerful conceptual foundation.
A closed loop.
Yeah.
Like the scientific method. Okay, I like that. Let's break down what each meta-ability means in their system. They use some notation, right? HRO.
Yes. H for hypothesis, R for rules, and O for observation. It helps keep things clear.
All right, first up, deduction. That's the one most people probably feel somewhat familiar with, I think.
Right. Deduction is defined as inferring specific outcomes, O, that logically must follow from given rules, R, and hypotheses, H. So the notation is H plus RO.
If this and this are true, then that must be true.
Precisely. It's about rigorous prediction and verification. If these facts and rules hold, what must be the consequence? It's about reaching certain inferences.
Okay, that makes sense. The classic. If all men are mortal, rule, and Socrates is a man, hypothesis, then Socrates must be mortal, observation. Pure deduction. What about induction?
Induction is different. It moves from specifics to generals. It's about abstracting general rules
Yeah.
from specific observations, O, and hypotheses, H. So H plus O are R.
Okay, so seeing lots of examples and figuring out the underlying pattern.
Exactly. It's the process of pattern discovery and generalization. You see multiple instances where a certain phenomenon occurs maybe with some initial guess or hypothesis, and you infer an underlying rule that seems to govern it.
Like observing that the sun has risen every single morning of your life. Observations. Maybe starting with a hypothesis that it follows a pattern, and then inducing the general rule that the sun rises every morning.
That's a perfect example. And crucially, it's probabilistic, right? Based on evidence, not logically certain, like deduction.
Right. And then there's abduction. This one always feels a bit more creative, maybe less structured.
It is often called inference to the best explanation. Given a surprising observation and a set of rules, you infer the most plausible hypothesis, H, that could explain why that observation occurred. So O plus R, H.
Finding the likely cause.
Yes, it promotes creative, backward reasoning. You see muddy footprints in the kitchen, you know the rules about how footprints are made and who lives in the house, and you abduce the most likely hypothesis, maybe the dog got in through the back door again. H, it's about forming plausible explanations.
Okay, got it. So deduction. Predicting effects from causes and rules. Induction. Finding rules from examples. And abduction. Finding the best explanation or cause from effects and rules.
And together they covered these different ways we reason to build understanding and test ideas, much like in scientific inquiry. This structured approach, grounding the AI training in Peirce's framework, is really the first key academic contribution here.
Defining the components. But how do they actually teach these?
Exactly. And the truly innovative part is not just defining these, but developing a concrete, operationalizable recipe for reasoning mastery, for AI, as they put it. They translate this conceptual framework into a practical three-stage training pipeline. This is where the academic novelty really goes from theory into practice.
Okay. Stage A, metabilities alignment. How do they go about actually teaching the AI these distinct skills, deduction, induction, abduction, and isolation? This sounds tricky.
This stage features a really clever technical innovation, the creation of a synthetic, self-verifiable task suite for each meta ability.
Synthetic and self-verifiable. Why is that so important?
Well, it's crucial for a couple of reasons. First, synthetic means the training data is programmatically generated. No expensive, time-consuming, or potentially biased human annotation is needed. That's huge.
Okay. Efficiency. What else?
Even more importantly, for teaching genuine skill versus just memorization, these tasks are designed to be out-of-distribution owed relative to the typical massive datasets LLMs are pre-trained on.
Meaning they look different from what the model has seen before.
Exactly. Different enough that the model can't just rely on pattern matching or recalling something similar from its training data. It forces the model to learn the underlying reasoning process, the actual still, not just memorize answers.
That makes a lot of sense. If you generate brand new problems that still follow the rules of deduction, say, but look structurally different, the AI has to actually apply the skill of deduction, not just recognize a familiar problem type.
Smart.
Very smart.
So what did these synthetic tasks actually look like for each ability?
Okay, so for deduction, H plus R, O, they use propositional satisfiability tasks. Essentially, the model gets a set of logical premises or rules, maybe a proposed scenario or hypothesis, H, and it has to determine if a specific statement or observation, O, is a logical consequence.
Like a logic puzzle generator.
Pretty much. The paper describes this as instantiating an iterative loop of hypothesis generation, logical consequence propagation, empirical inconsistency detection, and corrective refinement, which they argue directly instantiates the core structure of deductive reasoning. The tasks force it to chain logical steps and spot contradictions.
Okay, so it's forced to trace implications rigorously. Makes sense for deduction. How do they train induction, H plus OR, finding the general rule? For induction, they use something called mask sequence completion. The model is given a sequence of elements, numbers, symbols, whatever, with some parts hidden or masked. That's the O, the observation. It might get some initial context or hypothesis about the pattern.
And it has to figure out the rule.
Exactly. It has to infer the latent rule, or govern the sequence, and use that rule to fill in the masked elements correctly. The source notes highlight this really targets induction because the model must extract the underlying regularity governing the visible sequence and apply it to predict unseen values. It trains abstraction and generalization.
Okay, like a sophisticated what comes next in the sequence puzzle.
Right.
That's specifically designed to isolate that pattern finding skill. Cool. And abduction, O plus RH, finding the best explanation.
Abduction is trained using inverse rule graph search. Here, the model sees some observations, O, and gets a set of rules structured as a graph, R. The task is to work backward backchain through this rule graph from the observations to infer the most minimal, plausible hypothesis that could have led to those observations.
Reasoning backward from effects to likely causes.
Precisely. The source material explains this setup, induces repeated cycles of goal-directed hypothesis formation, verification, and revision, thereby fostering the core mechanism of abductive reasoning. It really teaches the model how to form and refine plausible explanations based on evidence and rules.
Wow. Okay, so they've built these incredibly specific, automatically checkable task generator synthetic data engines to train each distinct mode of reasoning. It's a very targeted form of instruction. How do they give feedback during this training? Is it just right-wrong?
They use a structured, rule-based reward scheme. It's actually pretty simple but effective. There's a format reward, just +1, if the model structures its output correctly, using the expected tags like think for its reasoning steps and answer for the final response.
So showing its work matters.
Yes.
Okay,
And
awesome.
critically, there's an answer reward of +2 for getting the task-specific answer correct. If it messes up the format or the answer, it gets negative rewards. This encourages the model not only to find the right answer, but to do so through a structured thought process.
And they mentioned curriculum learning.
Right. They start with simpler instances of these tasks and gradually increase the difficulty, which is a standard practice, but important for building up complex skills.
Okay, that covers Stage A, training these specialist models for deduction, induction, and abduction using these clever synthetic tasks. That feels like a really solid, innovative foundation. But how do they combine these separate skills into a single unified model? That brings us to Stage B, right?
Right. And Stage B introduces another notable technical contribution, parameter space merging. Instead of trying to train one giant model on all three tasks simultaneously from scratch, which could be difficult and messy.
Or trying some complex multitask fine-tuning.
Exactly. They take the weights, the parameters of the three independently trained specialist models, one for deduction, one for induction, one for abduction, and they essentially blend them. They linearly interpolate them.
So you train one model that's really good at deduction, another that's great at induction, and a third for abduction. And then you sort of average their brains together. Is that too simple a way to put it?
It's not a bad analogy, actually. The formula they use is pretty straightforward. Bermerge plus EI plus Li-A. Here it represents the model weights for each specialist, D for deduction, I for induction, A for abduction, and LRMs are just scaling factors, weights they tune empirically.
Ah, so it might not be an equal averaging. They found optimal weights.
They did, and the results were quite interesting. The paper notes the optimal weights they found were Leo 1.A for deduction, Leo 0.2 for induction, and Li 0.1 for abduction.
Whoa, deduction gets weighted really heavily there, like 5 times more than induction and 10 times more than abduction. Any thoughts on why?
It's a key empirical finding. It might suggest deduction is somehow more foundational, or maybe its learned parameters generalize better. Or perhaps it just reflects something specific about the tasks they used or the base model. It's definitely something worth pondering, but that's what they found worked best.
Interesting. So what's the big benefit of this parameter merging approach compared to other ways you might combine skills?
It offers some significant advantages. First, it's highly cost efficient. You've already done the heavy lifting training. The specialists merging their parameters is a relatively cheap computational operation compared to more training.
Okay, efficiency again.
Second, and this is crucial, the resulting merged model provides a really high-quality initialization point. It starts off with these foundational capability across all three meta-abilities already kind of baked in. This gives it a much stronger starting point for the final stage of training.
Which is Stage C, domain-specific reinforcement learning. Right. So this is where they take this new model, initialize with these merged meta abilities, and put it to work on actual real-world problems.
Exactly. In this final stage, they take that merged model, the one that now presumably possesses foundational deduction, induction, and abduction capabilities, and they fine-tune it using reinforcement learning on actual domain-specific data. They use data sets like math problems from the simple RL-Zoo dataset as a key example.
Okay. And the critical test here, the real proof in the pudding, is whether this whole process, the meta-ability alignment in stage A, the merging in stage B, provides a better starting point.
Yes.
And ultimately leads to a higher performance ceiling on these real-world tasks compared to a model that just started from a standard instruction-tuned baseline and went through the exact same domain-specific RL process in stage C.
Precisely. That's the ultimate validation. Does explicitly teaching these reasoning fundamentals actually pay off when you apply the model to hard downstream tasks like math or science problems?
So let's get to it. The results. Did this systematic three-stage process actually deliver? Did it lead to models that reason better on challenging tasks?
The empirical evidence presented in the paper seems pretty compelling. They looked at benchmarks across math, coding, and science domains, and the approach shows strong support. First off, even looking at performance just after stages A and B.
So after the synthetic training and the merging, but before the real-world math RL.
Correct. Even at that stage, the merged models already showed improvements over the standard instruction-tuned baseline on diverse, out-of-domain benchmarks.
Wow, okay. So that's impressive generalization right there.
Yeah.
The skills learned on those synthetic logic or pattern tasks are immediately helping somewhat on actual math or coding problems.
Yes. For their 7 billion parameter model, there was an overall average gain of about plus 2.5% across the benchmarks they tested. And at the larger 32 billion parameter scale, the gain was even more significant, a plus 3.5% overall average gain, and notably a plus 4.4% gain on the math average specifically, all before that domain-specific tuning.
Okay, so the learned skills are definitely transferable to some extent.
It seems so. The paper also includes an interesting oracle ensemble result. This is hypothetical. It imagines a perfect system that could somehow pick the best output from the individual deduction, induction, and abduction specialists for any given problem.
Like the ideal combination.
Right. And this oracle showed a potential gain of over plus 11% on the math average for the 7B model. It just highlights how complementary these different abilities are and the theoretical potential if you could perfectly harness all three.
That shows the intrinsic value of the aligned abilities themselves. But like you said, the most compelling result, the one that really speaks to lifting that performance limit, comes after stage C, after the domain-specific RL.
Absolutely. This is where they demonstrate the higher attainable performance ceiling. They ran a head-to-head comparison. Their model, which started from the meta-ability merged checkpoint and then underwent domain-specific RL, they call this domain RL meta, versus a baseline model that started from a standard instruction-tuned checkpoint and underwent the exact same domain-specific RL process, domain RL-ins.
So same final training, different starting points.
Exactly. And the results. The meta-line model consistently achieved significantly higher absolute scores on the challenging math benchmarks.
Can you give us some concrete numbers there? What does that higher ceiling look like?
Certainly. On the math benchmark average, the 7B domain RL meta model, the one with their foundation, reached an accuracy of 43.0%. The baseline domain RL-ins only reached 41.2% after the same RL.
Okay, so about a 1.8 percentage point gain just from having that better starting point going into the final RL phase.
Right, and if you look at the total gains over the original instruction baseline before any RL, their method achieved a plus 4.2% improvement on math for the 7B models, whereas the instruction-only RL approach only got a plus 2.4% gain. The benefit was particularly clear on more complex compositional math tasks, like those in the A dataset, which are known for requiring multiple reasoning steps.
And for the larger models, you mentioned a scalable advantage was highlighted. Did the gap widen?
Yes, and this is a really critical finding, potentially, for future AI development. At the 32 billion parameter scale, that performance margin did widen. The domain RL meta model reached 52.3% in math accuracy versus 50.3% for the domain RL-ins.
So now a 2.0 percentage point absolute gain in that final RL stage.
Correct. And comparing total gains over the baseline for the 32B models, their method yielded a plus 5.4% gain on math, while the instruction-only RL path achieved plus 3.4%. The key takeaway here is that the performance difference, the advantage from their method, increased with model scale.
Okay, that's really interesting. It suggests This isn't just some small tweak that helps a bit. It's a foundational improvement that provides a better starting point, and it enables larger, more capable models to reach significantly higher levels of performance after that final targeted training.
That's exactly the argument. It's not just a marginal improvement, it's a demonstrable lifting of the ultimate capability ceiling, and the bigger the model gets, the more this foundational alignment seems to matter. It feels like a very strong argument for this systematic, explicit approach over just relying on emergence.
It really does. Did they do anything to check if the models were actually using these skills? Like, did the improved performance actually come from more deduction or abduction?
Yeah, they did. To further validate that the training worked as intended, that the models actually learned and were using these distinct reasoning skills, they conducted behavioral analysis. Using diagnostic frameworks and tools, they confirmed that their meta-ability-aligned models show a, quote, markedly higher frequency of deduction, induction, and abduction behaviors in their internal processing compared to the baseline models.
Okay, so there's evidence linking the performance gains back to the acquisition and application of these specific reasoning skills they trained for.
Exactly. It helps confirm the mechanism.
This all points towards a potentially significant shift, doesn't it? What are the broader implications here, moving from hoping for those emergent aha moments to systematically teaching the actual building blocks of reasoning?
I think it means we potentially gain a path towards AI reasoning that is much more predictable, much more interpretable, and perhaps more adaptable as well. We're moving away from relying on unpredictable emergence towards what the paper terms a modular, self-verifying paradigm.
Okay, predictable because you've explicitly trained the skills you want it to have. That makes sense. Interpretable. How so? Because the skills are trained as distinct modules.
Potentially, yes. Having these distinct modular abilities might allow for finer-grained analysis of how an AI reached a conclusion. You might be able to trace whether a key step relied more on deduction, induction, or abduction, for example, and adaptable. How does this approach make AI more adaptable?
Yeah, what's the adaptability angle?
Well, because this modular approach allows for tailoring, you could, in theory, inject additional desired capabilities into the model, maybe train another specific reasoning skill using a similar synthetic data approach, and then merge that in too. It gives you a potential mechanism for endowing the AI with specific reasoning competencies as needed for different tasks.
That's interesting. And there's also that huge practical benefit you mentioned earlier, resource efficiency.
Absolutely. As we discussed, the synthetic, self-verifiable tasks mean no additional human annotation is required, which is a massive bottleneck and cost in traditional AI training pipelines.
Right. And maybe having these somewhat modular skills, like distinct deduction or abduction components, could make the models easier to audit or debug, potentially improving safety and reliability, because you might have a better handle on which reasoning mode led to a particular, maybe problematic outcome.
That's the hope. It certainly lays a much stronger foundation, conceptually at least, for building reliable AI systems compared to hoping complex behaviors just emerge correctly. The potential applications are vast. Imagine, say, scientific discovery workflows where an AI can reliably generate hypotheses using abduction.
Then rigorously test those hypotheses using logical rules via deduction.
And then generalize findings from experimental observations using induction, all in a structured, controllable way, not just waiting for a lucky flash of insight from the model.
That really does feel like a fundamental shift in how we could approach building truly intelligent systems.
Yeah.
So just to sum it all up, this paper presents this novel, academically grounded, three-stage pipeline. First, explicitly align large reasoning models with foundational reasoning meta-abilities, deduction, induction, abduction, using cleverly designed synthetic self-verifiable data.
Stage A.
Right. Then, efficiently merge these specialized skills together via parameter interpolation, stage B.
Getting that strong initialization.
And finally, fine-tune that merged model on specific real-world domain tasks using reinforcement learning, stage C. And the key finding is that this systematic approach yields demonstrable, scalable performance gains. And maybe most importantly, it seems to raise the attainable performance ceiling for these larger models.
Offering a path towards more predictable and controllable AI reasoning, yes.
It really makes a compelling case for teaching AI how to think in a structured, fundamental way, rather than simply scaling up data and parameters and hoping complex reasoning figures itself out on its own.
It definitely pushes in that direction.
Which leaves us with this thought to maybe ponder. If systematically teaching AI fundamental modes of reasoning like deduction, induction, and abduction through methods like these using synthetic data, parameter merging, if that leads to more predictable, controllable, and ultimately more capable systems, what new kinds of complex problems might become accessible to AI? problems that were previously maybe out of reach precisely because of the unpredictable nature of those aha moments. What possibilities does this level of reliable, controllable reasoning actually unlock for the future?